This is capsule 2 of general chemistry series, so this is the unit 2, and we're going to be covering the atomic structure developments, which is the scientific experiment that was done to find out about mainly the electrons, but the atomic structures in general. And then there is many theories that were discovered by different scientists about how electrons behave. So they are wave-like elements, and they could be either particle-like or wave-like behaviors. And when we know one, we will know less about the other. And so when we see that there's more of a wave behavior, there's less of the particle behavior, and when you see more particle behavior, we see less of wave behavior. There are all these kind of photons and light and absorbing energy kind of theories are explained, but they're not too important, as my final exam did not have anything about it and no tests on it. But we do mention it, and it is a part of the basics of what we could call the quantum versus mechanical theory in terms of electrons. But either way, you could just know, well, it depends on the what the teacher will teach you, but primarily that atoms have a center that is hard and a void of nothing, or like an emptiness inside with electrons, and that the center is a plus, where a center is positive, and that the outside is a negative, which is the electrons, and that the electrons have more of a wave-like behavior. And we'll see that a lot in this chapter. So this is, well, for me, unit 2, but it could be perhaps chapter 3, depending on what we learn, what you learn. So unit 1 consists of topic 1, which is the basics of atoms and molecules and elements, periodic table. Topic 2 is the stoichiometry, so all the balancing equation, and finding reagents, so reactants, products, comparing the products to how much reactants we have in terms of percent economy, in terms of theoretical and percent yields, which one's the limiting reagent, the IFR table, that kind of stuff. And unit 2 is these, starting off with the scientific experiments that were done, and then we do the models. There's a lot about the model in terms of electron configurations and how the electrons are placed in the atoms, and we're going to look at different atoms and different elements and how the electrons are placed. Everything about the 3D positions of the electron is what we're going to be looking at, and that it is not a flat drawing like this that we used to learn in high school. And no, it is not a 2D plane. The atom is much more complicated. We could think more of it as like a 3D like this, but it's not that simple either. And after that, we're gonna be covering, well, it's just primarily the positions of the electrons. So let's just start right into it. We have to first know the word quantum. And quantum basically means the science that was not explained by the mechanical theories. So the mechanical theory, for example, is that the light will go straight like this, and it will hit a certain wall, and it will hit a certain surface. But that does not explain all of the reactions that these atoms are able to do. So like the reactions, the chemistry itself cannot be explained merely by the mechanical theory. And that's why we have to add what we came up with, the quantum theory that does explain these behaviors. And primarily we said that it's just basically wave-like movements of the electrons. But the point is that it will somehow reach the other side by not a straight line, but a bit of going everywhere, and that's why we say that's like a wave line, and still end up at the same spot even not by going like a straight line. That's kind of the whole principle. We can talk about the carton that has 2 holes and there's a beam of light. If there is a wall here, well, normally thinking it would be like a two spotlights like this, right? But then that was not the case in terms of the quantum lights, so it ended up rather being just dots everywhere, meaning that the light does not just travel straight and go like that. There are some other behaviors that are going on, and that is going to be explained by the quantum mechanics, or the quantum mechanics, at least of the atom. And to understand that, we need to know the quantum numbers. And quantum numbers are what describes the position of the electron in the atom. So every single atom has a set of numbers that describe their position in the atom. And we'll start with the principal quantum number. The principal quantum number is the n. It's represented by the letter n, and it could be of 1, of 2, of 3, and then these are levels. The principal quantum number describes the level, the energy level of energy of the electron, or specifically the electron's orbit. And the electron orbit is basically the number of the orbital. So if we draw it in a circle like this, we'd say that the first level will be of n1, the second level will be of n2, and the third level will be of n3. This is a very simplified version. Do not remember it this way, but in principle, it's like that. Every time we jump up, it's like jumping up a new level of energy that the electron has. So the energy is lower in the center and higher on the outer side. So the energy is decreasing as we go out. Energy is decreasing as we go out and increasing as we go. Yeah, so the energy of the electron is smaller in the further orbit, and that is because the electrons have negative energies. So the electrons are negatively charged, so the bigger they are, meaning the less negative they are, well, obviously if it is less negative, it is bigger, so it's bigger at the center, and if it's bigger, they're more stable. And the lower energy, so smaller, they're going to be a less stable, and this is due to, again, the energy being negative, and if it's a smaller negative, the absolute value of the energy in the center is smaller, but then if it's a smaller negative, well, then it is higher, so the energy is bigger, and if it's further, it is big. Well, if it is higher in the center and smaller in the further, because absolute energy that is negative will be smaller, because a bigger negative number, so if there's a 0, the bigger negative number it's a smaller energy. So the whole principle is that it is more stable at the center. So it's more stable as they go lower or go towards the lower n level. So that's the n number. N starts with 1 and just goes to 2, 3. They're all integers. After the principal quantum number, we have the angular quantum number, which is represented by the letter L, and the L always has to be n minus 1. So if it is a 1, it would have L as a 0. And if it is number 2, for example, it will have the L as 1, and if it was a 3, then we have L as 2. And every time we have the ones that are, so it's the 0 is the extremity, 1 is the extremity, and 2 is the extremity. So we actually have 0 and 1, 0 and 1 and 2. So these, if it's a 1, it will only have 0 because it has to be an n minus 1, and anything smaller than n minus 1. So 0 to n minus 1. 0 to n minus 1. So the L of 0 is also represented as the letter S. So S orbital. And if it is a 1, it will instead be a p orbital. So 0 is still S orbital, and 1 will be a p orbital, and 2 will be a d orbital. And what these S, P, or D mean is simply the shape of the orbit that the electron's in. So, like I said, the electron structure, the electron configuration, we call it. The configuration means, well, the specific position that each electron is on will depend on which, of course, principal level, but also the second principal, or she said the sub-level orbit it is in. So it's the angular, the L number. In each n level, there could be different L levels, depending on what the n is. So if n is equal to 1, well, L will only be 0. But if n is equal to 2, L could be 0 or 1. So what happens is there could be electron that has n equals to 2 and L equals to 1. And there could be electron that has n equals to 2 and L equals to 0 as well. So all this to explain that we could actually draw the atom like this. So this is the nucleus that has protons and neutrons in it. And the first layer is always a S, which is L equal to 0. And of course it is n equals to 1 because it's the first level. So the electron on the first orbit here is of n equals to 1 and L equals to 0. The sub-level, so the principal level and the sub-level is n equals to 1 and L equals to 0. Now, this L will represent what the orbit looks like, the shape of the orbit. S orbit looks like a circle. L orbit looks like a dumbbell. A dumbbell could look like that, or like that, or like that, like 3D. And we also have d orbitals that now you don't need to know exactly what they look like, but it is instead like this. So again, they could have different orientation. They could look like this, etc. And there's the F, but their drawings are a lot more complicated. So you primarily only need to know the S level and the L level. So again, S is when L equals to 0, and L is when... Oh, sorry, it's not L, it's P. P level, sorry, is when L equals to 0 if it's a S, and L equals to 1 if it's a P, and L equals to 2 here, L equals to 3, and so on. But you primarily only see S and P, and maybe D. But for drawing, you only can know S and P. So right now we have the first electron like this, and it would be another electron. So usually in one orbit, it can have 2 electrons. That's another law that we're gonna later cover. And the p orbital, now we don't have a p orbital in the n equals to 1 because the L number is 0 to whatever the n number is minus 1. Well, 1 minus 1 is 0, so it just comes back to 0. So for n level, there is no p orbital. You can find that out by using the formula of the math, the math of the formula. So now moving on, we have a new orbit. It's n of level 2. So now the level decreased, or we should say the negative energy decreased, but what the negative energy, it's less negative, so it's a smaller energy, so less negative. Further they go, less negative, so the energy is smaller. The negative energy is smaller since electrons are negative. And we have L equals to 0 or 1 now. We do have the 1 because 2 minus 1 is equal to 1. And we remember that L numbers are 0, 2, and minus 1. So if I draw the first electron, this one is going to be L equals to 0. And that is going to have N equals to 2, L equals to 0, and it's a s orbital because it's in a circular shape orbital. And now we can have another one here. But now we're going to move on. N still equals to 2, but L is now going to have 1 because we do have a 1. Now 1, we know that looks like a p orbital. So what's going to happen? There's going to be p orbital like this. Now we have a p orbital. And the p orbital has 3 orientations, so you will be drawing it like this. And that's all the p orbitals we have. So this is a n equals to 2 p orbital. And then now we have the d orbitals that is not included in n equals to 2 because, well, you'll learn that when n, well, we know still, again, was the formula, L number has to be 0, 2, and minus 1. When n is equal to 2, well, 2 minus 1 will become a 1. And we do not have a 2 for the L to be equal to d. Well, the L equals to 2 is a d, but we do not have a L equal to 2, so there is no d orbital here. If we keep going, it's basically going to look like this. So that's the nucleus again. S equals to 1. L equals to 1 and n equals to 1. This is another s orbital, but level 2. Now p orbital, still level 2. And then moving on, s3. So n equals to 3 now. And it's a s orbital because L equals to 1. And we still have more p orbitals, but now they're bigger. And then now we have d orbitals because 3 minus 1 is a 2, and there is d orbitals and n equals to 3 level. What is that going to look like? Well, they're a clover type. That's one d orbital, another d orbital, another d orbital, and they're in different orientations. So you realize that it looks like a bundle of lots of I don't know, circles and dumbbells, and that's what the atom looks like, and that's why it becomes like a 3D shape. And the electrons could be basically anywhere amongst these orbits. And the L quantum, the angular quantum number, L, I already wrote it here, is the shape once again, and it could look like these. Whereas N is the level, energy level, or we could say the orbit layer, which orbit it is. It's the first one, and it's the most closest to the nucleus. If it's the second one, it's second closest. If it's the third one, it's just getting further out. So now we know the N number, the L number, and we still have more. We have the ML. So the ML is, I kind of subtly didn't mention it in the end, used the ML without specifically naming it, but the MLs are these. So there's 3 sets, right? Because there's a X here, let's say, and a Y here and a Z here. They're just orientations. You don't need to specifically know which orientations these are because if it was in space, there's no up or down or right or left. Depending on which point of view you are in, the left could be a right of someone else's. So basically, you don't need to know exactly which orientations they are, but you should definitely know that ML is of absolute value of the L from negative to the positive L. So let's say if L was equal to 3, so then the ML will be minus 3, minus 2, minus 1, 0, 1, 2, 3. So those are the ML. They just mean the orientations. So in this case, it will have 1, 2, 3, 4, 5, 6, 7 orientations. Orientations just means, is it like this, or is it like this, or is it like this, or is it coming into the page or out of the page? They're just many ways that the specific L-shaped orbital could look like in terms of how they're oriented, how they're tilted. It could look straight, it could look upside down, towards the left, towards the right. So ML number is minus L2 plus L. And that's it. So if they're giving you an N, you can actually find the possible ML numbers, the set of ML numbers. If they give you L, you can find the exact ML numbers for that orbit. And they will give you sets of numbers that you have to identify whether they are right or wrong. So if such combination is possible or not. And that's basically following each rules. 0 to n minus 1 for L, and if it doesn't follow that by the set of numbers that they give you in the question, then it's a false. And if that's still clear, you can just move on to ML, see if it belongs in the minus L to the plus L. This does include 0, by the way. It does include the 0. And lastly, we have MS, is a spin. Spins are usually plus half or minus half. Yeah, plus half or minus half. It means spin up or spin down. And this will be further clarified, but usually we have 2 electrons in one orbit, right? So one of them will be spin up, so MS is plus half, and the other one will be spin down, so MS is minus half. What matters here is that we have to fill in a certain order, that we have to consider the spinning, if it's spinning up or down. And that is going to be a lot more clear if I talk about the orbital boxes later on. So we're just going to stop here for quantum numbers. So quantum numbers, the plus and the minus here has nothing to do with N or L or ML. It's just that it could be either plus or minus. Can't be both. Can't have 2 pluses in one orbit, or can't have 2 minuses in one orbit. It has to be one is plus, the other one is negative. So one electron will either be positive or negative, and either way, it's not wrong. It is not wrong to say that one is plus or that the other one is negative. Another point you should know is the ML. The ML can be literally anything. So the ML, as long as it follows this and minus L to positive L domain, I should say, minus L to positive L range, there is no specific which ML value it has to be in. There is no, one electron looks like this, the electrons right here, it looks like it's straight, so it has to be a Y, so it should probably be like a 1. No, there is no specific ML number for an electron other than everything having to fit in there. Of course, there can't be a something that's smaller than minus 1, something that's bigger than plus L, that's for sure no. But as long as it is in the range, it does not matter which orientation it is in. Again, because of the spatial concept of, if you were floating in space, there's no up or down or right or left. So 3 factors that you have to know that is going to do something called the splitting, or we should say the electron configuration. The electron configuration is how the electrons are positioned and spread across the map of the atom. So like I said, it looks like a huge mess of so many orbits that are getting bigger as the level gets bigger, and that has many more orientations and just a lot complicated orbitals, each of them that has the configuration of NL, ML, MS. And this one is the configuration here does not totally explain. Well, the simplified drawing that we usually do in high school of the 2D drawing like this does not completely explain because of the factors of splitting. So splitting means that the electrons each other will repulse themselves, so the negative electron and another negative electron will be pushing against each other, so then there's going to be a space a bit further than expected. And furthermore, there could be the attraction of the nucleus and the electron, so the electron could be closer to the nucleus than expected. So all of this is to explain that it is not following the standard what we think they do, because there are other electrons, as we can see in here. If each orbital had 2 electrons, there's like so much electrons here, and each other will interact. They will not just do nothing against each other. They will still have repulsion, they will still have attraction towards the center, and all of this will make the electron configuration, or we should say the positioning of the electrons, not exactly what we expected it to be. And the only atom that does turn out what we expected it to be is hydrogen. And hydrogen, it's actually iconic to say this, but of course it does respect the basic theory of what the electrons should look like, because there's only one electron. If there's only one electron, there's no interactions amongst, well, non-existing other electrons. So hydrogen is the only one that follows the mechanical or the energy orbital that only depends on one electron. So other than that, so basically every single other atoms will follow 3 principles. The first one being the Coulomb's law. Energy equals to, the simplified version is Q1 Q2 over R squared. Q1 is the positive charge, second Q2 is the negative charge, divided by, this is the distance. So if they are both positive, then it's going to be a positive positive energy, and if it's a plus and a negative, it's usually always a negative energy. Either way, you just need to remember that the smaller the distance, the bigger the energy, so they're more attracted, since it is the division, as you can see. And the bigger the charge, so let's say a +2 and a -2 is a bigger charge than a +1 and a -1. So the bigger the charge, the bigger the energy, and that's obvious as it is on the top of the fraction. So we can also see that since it's squared, the distance is more dominant. So if it's far or close is more dominant than if the charges are bigger or smaller. Second one is the shielding. So the Coulomb's law here just explains if the energy of attraction is small or big, depending on the charge of the ions. And, well, ions, because let's say KCl will be a plus ion and negative ion, so the charge of ions. And comparing it to the distance, or we should say the size of the atoms, if they're sticking together, the size. So the size is basically the radius of each of them, therefore telling us the distance between apart. So that's the energy of how much they are attracting each other. Shielding is the electron repulsion. One, two. So shielding is, well, actually we should rather say, let's say if there's it's a very, very easy concept that a positive charge is in the center, and there is some electrons over here, and there is an outer valence electron. Let's say there's 2 over here. If there are electrons in the central orbit, well, they will sort of absorb or take away or shield. We say shield the positive energy or the positive attraction that these outer electrons will feel. So because of the electrons in the center that kind of block the positive attraction, the outer layers will feel less of the nucleus positive attraction. And that is stronger as the layer adds on. So a layer, let's say there's like 5 layers and there is an electron in the last or the outer layer, well, they feel a lot less of the neutrons, well, the center's positive attraction, because it's so far and because there is so much shielding going on. So all these electrons, they are making it feel less of the positive attraction from the center. That's what the shielding means. So there's also the repulsive charge of electrons and electrons amongst themselves. So there is constant pushing each other among the negative electron and the negative electron. So then what happens is that they're going to be a little bit like more spread out, and there's basically the instability or it could be stable in contrary if there is a 3 single pair. Later on we're going to see, but either way there are these 2 factors, and the third one is the penetration. The penetration is if the electron penetrates the cloud of, let's say, a 1s electron to get closer to the nucleus, it is less shielded and feels greater positive energy or nuclear energy, and therefore it's a lower overall energy. If an electron, let's say this is a cloud of electrons and that's the nucleus, well, one that is closer to the nucleus will of course feel a stronger pull towards the electron. So then if it was like this, so the penetration means that it is approaching the nucleus. It's like forcing the electron to approach the nucleus, but the closer it is, basically the more attraction will feel. So everything that is doing the shielding, we call them core electrons. There is a diagram that you have to know. It will probably be easier if you see in class, but basically there are energy, well, actually not energy, the radial probability graphs. So radial probability means how probable an electron will be found at a certain distance. So these are our radius distance. This is the radial probability. So how much probability is there of an electron to be found at a certain distance from the nucleus? And these will usually look like waves of mountains like this. And you can see that there is these little hills that are very important, and the next one will be this, and then the next one will be this. For example, these are the S1 or 2P or 2S, 1S I should say, or I don't know, 3S, 3P, 3D. Each of these waves will belong to one of these guys, and what you have to understand is that there is the most probability to find let's say the most probability of this wave right here, this wave I should say, is here. That's the highest one for this wave, this particular wave, but there is a little bit of percentage here, probability here that isn't too high, but still is existing, and it is closer. And for some reason, there is a dominant probability that this one will be the position of this, let's say, 2p orbital. So there is many theories and reasoning to why the electron will be positioned in such way and not the other. And there are ones that are not obvious because it would usually look like a certain position, but turns out to be another. And these type of graphs are what explains perfectly. It will explain the filling order of orbitals and the position, just all the quantum numbers. As long as you know your quantum numbers, you're able to justify it, but without using the quantum numbers, it will be these graphs. So these graphs actually will explain the set of numbers if you work backwards. A few principles to know. The first one is off-ball principle. The off-ball principle is to determine the configuration of the next energy orbital or the next orbital that is going to be filled. So the order is a 1s, 2s, 2p, 3s, 4s, 3d, and realize that it's 4s after 3s and before 3d. And this is explained from these graphs, but you just need to memorize that 3s, 4s, 3d, 3s, 3p, sorry, 3p, and then it's 4s, and then it's 3d. So after 3p is always 4s, filling order, and that's just the order you have to memorize. There is an explanation to this, and it is basically because 3ds are transition metal orbitals, and depending on the teacher, they will explain it to you differently, but you can just listen to what your teachers teach you, I suppose. And filling order actually follows the taking out order. The taking out order is to say the ionization or just removing order. The order that you fill it in will be equal to the order that you take it out. So if you have a 3p and then a 4s and then you have a 3d, so these are the transition metals. So the d orbitals are here. These two are s orbitals. These will be p orbitals. And f orbitals are here on the bottom, which are the lanthanides and actinides, I think. So the filling order is always s, 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 and then after the s of, let's say, the fourth level, which is the fourth column, we jump into d of the third level, so 3d here. And by the way, this is like the first row is a 1, the second row is a third row is a 3, and then now 4, which are these are the end levels. So the filling order is 4s here, a 4s here, and then a 3d here, and then 4p, and there's 6 p's, 5 p's. So no, sorry, 6 p's, because p's are 3 ml numbers. And then after that, the filling order is 4s and then 3d, but then when we take it out, we actually take out 4s first, and then we take out 3d. So it kind of follows 3p filled in, 4s filled in. So then now if you take it off, it's like the same logic of taking out 4s since we filled in those last, and then we take out the 3p's. No, sorry, I meant here. So you filled in the 4s and then you fill in the 3d. So then when you take them out, you take out the 4s and then you take out the 3d. So first you take out the 4s and then you take out the 3d. So either way, it's always 4s first and then 3d after. The d orbitals are after, regardless of filling or taking it out. And then we have the Hund's rule. This is all about singly filling first. With parallel spins. So that means we can actually represent these orbitals with boxes. This is an n orbital, this is a p orbital, and we'll stop there actually. So let's say there's two n orbitals because this is a 1s and this is a 2s, and the p orbital will make it a 2p orbital. The order of filling means the order of putting in electrons into these orbitals. So in box form, we can just draw an arrow like this, meaning that's the first electron. And then we will put another one that's like spin down. So let's realize this is the spin up, which is the plus 102. The second one is the minus 102. And after we do a 2s, exact same thing. But when we come to 2p, we have to first singly pair like that. All spin up and then spin down. So everything spin up first, and then you feel them spin down. But if there isn't that much electrons, of course, you could stop there. Or if there's another one, it would be that. And then the next atom will be here, electron. And the electron will be here, and etc. So everything first singly paired. It could have 5 like this if it's a d orbital. Everything is first singly paired, and then the second electron is going to be filling the full pair. So that's the Hund's rule. And each electron that's added just means the next atom in the periodic table. So we're just moving on to the next atom in the periodic table. That's the Hund's rule. And Hund's rule also explains how, well, not explaining, but also mentions how the, let's say, 2p here is going to be actually 2px, and the 2py, and the 2pz, let's say, because of the orientation of what they look like. These are degenerate. Coming back to the space explanation of how orientation just depends on from where you're looking at the point of view, but there's no up or down or right or left in space. Well, they're degenerate in terms of they have the same energy. So regardless of if it is a 2px orbital, 2py, or 2pz, they all have the same energy level because it's a 2p. All 2p's, so the 3 here have the same. And if it was a d orbital, it's going to have 5 orbitals like this, so 5 boxes. 1, 2, 3, 1, 2, 3, 4, 5. So this is, oh no, that's a 6. It's just 5. 1, 2, 3, 4, 5 boxes, and each box just represents one orbital. Now we could actually start drawing configurations. So we can look at your periodic table, and let's say the hydrogen is a 1s1. 1s1. The 1 here just means how many electrons there is in that orbital. In hydrogen there's only one, so it's gonna look like this. And He, well, helium, it's a 1s2. So in the 1s orbital, this is the 1s. The 1s orbital, there's 2 electrons. So I wanna draw it like that. In the lithium, there is a 1s2 and 2s1, meaning that there is a full 1s orbital and and 2s, but there's only 1, so no 1 electron in there for lithium. And beryllium, we have 1s2, 2s2, so this is a 1s that's full, and a 2s that's also full. And you just keep on going like that for, let's say I give carbon C. It's gonna be 1s2, 2s2, 2p2. If you look at it in your periodic table, you can just count. So hydrogen's 1, helium's 2, the second one. So those are the first two over here. And then we have lithium, that is 1s2, 2s1, and then 2s2, 2p1 for boron, 2p2 for carbon, and then 2p3 for nitrogen, 2p4 for oxygen, 2p5 for fluorine, and 2p6 for neon. And that's just gonna look like this, for example. So then neon will look like these two first ones, and these ones. First fill them in singly paired and then fully paired. And this is a noble gas configuration because obviously they are all full. Everything is full, so it is very stable, and reactions are really rare with noble gases. And noble gases configuration can be the shortcut for, let's say, let's do an arsenic. If you do arsenic, it's quite far, well, not that far, but it's somewhere in the middle of the periodic table. We're not going to write 1 is 2, 2 s 2, 2p6, and then 3s2 and 3p6, and then 4d10, and then like it's gonna be too long. So what we're gonna do is write Ne with a bracket around it, meaning everything until Ne, or actually it should be argon, everything until argon, which is right under Ne, the neon. And then we start off with 1, 2, 3, 4, so 4s2, and then we have a 3d10 because all the transition metals are filled, and then 4p3 since arsenic is in the third p orbital. So box wise will look like 4s 2, 3, 4. That's a 3d10, so everything is paired. That was a wrong way to draw it, actually. It should rather be everything paired up first and then fill it in. But now I knew that everything's gonna be full, so. And then now we have the p orbital, 4p, level 4p orbital. So just 3, and everything is everything is singly paired. Like this. So that's gonna be the configuration for arsenic. And you can do that for as many as you want to for exercise. Just a few notes important to know is chromium and copper that are really particular. So if you look at chromium, they have configurations that are a bit more special, but they're irregular, and they don't just follow the normal rules like the Hans rule and the Pauli principle rule that we looked at. So if we do chromium, where's chromium? So if we do chromium, it has an argon as a noble gas to do our shortcut, and usually we would say 4s2, and after that 1, 2, 3, 4, 3d4. But that would be box wise, it will look like 2, 4s, and then my d orbital, it will have 1, 2, 3, 4, and this is really unstable. They want this extra electron here to go over there and instead be all singly paired, and that kind of looks nice to human eye too, no? Like if there was one box missing and there's 2 here, maybe we want to bring it so that everybody has 1 electron. Well, that's what chemistry decided to do. That's what nature decided to do. So this is wrong. Chromium will rather be Ar with 4s1 and 3d5, so that everything is singly paired. Similarly, for copper, it will be AR 4s1 and 3d10, because if you fill it in normally, you would see that there's 2 here, and then there's 9 for copper in the d orbital. But realize that there's one space that is empty, well, not empty, single. That one of the boxes in this d orbital is single. We want this one to be fully paired, so that's maybe more satisfying. What's actually about satisfying? It's a lower energy level. Lower energy level means that they're more stable. And I don't think you have to explain why this is a lower energy level, but you could go nerd it out with a chemistry teacher. I actually went to try asking. He just said that it's just more stable somehow. Yeah, I don't think he gave me a clear answer. Anyways, this one will be moving over here, and this one will be single, so 4s1 3d10 is the correct answer. So these two are the exception, the main ones that you need to know, but there are other ones. You can look at it in detail because there are periodic tables that show you the configurations. But those are the main special cases, so CR and CU. Now let's talk about diamagnetic and paramagnetic. This just means if the boxes are all paired or not. If the boxes are all paired, it is a diamagnetic. If one of the boxes, even just one, is not fully paired, and it's a paramagnetic. And if let's say 1 2 3 4, let's say they are all singly paired, of course it is not fully paired. If there is one box that's singly paired, it's still not fully paired, so they're all paramagnetic. The ones that are diamagnetic are noble gases and some other particular cases that it turned out to be a fully paired. So it could be let's say Cl minus, so it gained one electron and become a configuration of argon, but it's a chlorine minus, so that is fully paired. So every box is fully paired, and it is diamagnetic. Otherwise, usually in the big probability it's paramagnetic, but you just need to look at the box diagram. Now we can look at periodic trends. It's all about sizes, electronegativity energy, ionization energy, electron affinity, and the metallic character. What did I not say? The Z effective, things like that. And this is basically logic if you understand it one by one, but I did take some time to understand it myself. The radius, for starting off with the radius, is a trend getting bigger that way, and it's smaller here. And this is a bit of a logic, I could say. If you draw the electrons, or if you draw the atoms, fictionally speaking, the more you go this way, we're going to add electrons on the same orbit, meaning that it will be more compacted. If it's more compacted because the electrons are more and more, well, there's more protons and electrons actually going this way on the same orbit, where the electron is a valence electron, it's on the same orbit, so the same valence electron orbit, it's going to be more attracted, right? Because if there is a lot of protons and increasing electrons on the same orbit, well, then the attraction is going to be stronger, so the atom will become smaller. So it becomes smaller as we go to the right side, first off. If we go down, it actually gets bigger because layers are added, and if there's more layers added, well, naturally will just get bigger. So that's why the trend is smaller to the left and bigger to the down. So that's the trend. So radius trend, the arrow is always pointing towards where it is increasing. So just remember that. This is a must know for this course. And now we have the ionization energy. Ionization energy is the energy required to take off an electron. So to ionize, well, it's only talking about taking off an electron, removing an electron. And removing an electron is easier on a bigger radius. And that is logic as well, because if there's a center here that's positive and there's so many layers and the radius is so big, there's an electron right here, it's easier to remove this one than to remove this one, like obviously, because it's so attracted to the center, whereas this one is only a little bit attracted to the center, also because of shielding of the other electrons, of the distance, you know, the Q1, Q2 divided by R squared distance. If it's a bigger distance, then the energy that's attracted is much smaller. Either way, taking off an electron that is far is easier than if the electron was closer. So it is an opposite trend to the radius. Opposite trend to the radius. So the trend of the radius is going down to the left. The ionization energy, the energy required to remove an electron, is that way. Higher on the right top and lowest on the left bottom. So it's easiest to take off. So lower energy of ionization energy, easy to take off, and this is hard to take off, which makes sense because noble gases should be harder to take off. Noble gases are ones with fully paired or fully boxed. All the electrons, well, all the boxes are fully paired and there's no box that is single or empty. That's ionization energy. And we need to know that these energies, the ionization energy is a positive energy. So it's a positive, it's an endothermic energy. And that is because it is required. Energy is required to remove, because a work needs to be done to remove it. It's not a gaining energy by removing electron. Removing electron requires energy, so it always absorbs. So it's a positive energy, since it needs to absorb the energy. The iPad. There are a few exceptions for the column of BE to B, of NO to of N to O, of MG to AL, and of P to S and AS to SE. So if let's say the B, E, and B, for example, we have 1s, 2s, and then a 2p, right? If we have a 2p orbital that is singly paired, it's actually easier to take off this one to take off this one here. So then the trend will be that B, the boron, will be easier to take off than BE. So in this case, it's the opposite trend. So because it is singly paired in the 2p, BE is easier than BE. The boron is easier than beryllium. I should just say the names. And for nitrogen and oxygen, well, nitrogen has a all singly paired 2p orbital, whereas oxygen is like this. So this one is all singly paired. All single pair is like a triangle power. It's like a trio power, that 3 single paired 2p orbitals are very strong and stable. Depends on what your prof wants to teach you again, but in what I learned, it's basically that these 3 are just stable because they are all like opposing each other, and they're stable because all of them are singly paired, so they don't want to add another one. Like adding another one requires more energy. So here we are not 3 single paired. There is one that is fully paired and 2 that are single. So then removing this one is easier then removing the very stable 3 single paired 2p orbital. So now oxygen is easier to remove, even if in the trend it says otherwise. So these are all exceptions. Now Mg and aluminum is the same thing as the beryllium and boron. P and S is the same thing as the N and O, and arsenic and selenium is the same thing as the nitrogen oxygen as well. So this is all exceptions in the trend, and these are the main ones. So as long as you know these or the logic of these, that if it is this kind of configuration, it's easier to take off 2p than 2s, and the fact that 3 single paired is very strong. As long as you know these two, the exceptions are quite handy. Yeah, just remember, easier to remove spin paired. Spin paired here, they're paired. It's easier to remove these guys because there's a repulsion between them. There's a repulsion between these two electrons. And moving on, we have the electron affinity, the EA. So for EA, the trend is the same. I remember. Oh, EA is just usually going to the right, actually. You don't need to know. There's no exact electron affinity trend, but usually to the right, it is more exothermic. Exothermic. Meaning, well, first of all, electron affinity means the energy change for adding an electron, and adding an electron would usually be exothermic, and it could be endothermic depending on the situation of the atom, but it is exothermic because it releases energy by adding an electron. Electron adding is usually exothermic, as taking it off is endothermic, so it requires energy to take it off and will release energy when it is combined. And we say that it is more exothermic to the left because it is more electronegative. Electronegative means that an atom wants to gain that electron, like it more wants to gain it, so it is more aggressive in attracting a negative electron than, let's say, a calcium. Calcium will more want to get rid of 2 of their valence electrons, whereas chlorine, for example, wants to it's just missing 1 electron, so it is really high in electronegativity. Electronegativity means they're wanting for a negative electron. They want more electrons. So it will be all the noble gas approaching electron negativity is basically how eager they want an electron, so how much they attract a negative electron, and therefore, well, it's not directly associated, but electron affinity is the energy change, so it is more exothermic approaching the right. Another exception here is of group A5, which is the group of the nitrogen period, so nitrogen and everything to the bottom. Let's say a nitrogen and oxygen. Let's say an oxygen and a phosphate. Oxygen versus a phosphate, or I should say oxygen and a phosphate, because this is what it looks like on the periodic table, is actually easier to add an electron on oxygen than on phosphate, which contradicts the what? Yeah, so this again is about the trio power. If there are 3 singly paired electrons on phosphate, for example, it is harder to add, just like it is harder to remove an electron. So it's harder to add on a singly paired trio on the 2p orbital than to add on to the oxygen that already has 1 pair. So this is a lot more stable, and this one just therefore acquires an electron with less energy that is released. Oh, sorry, no, more energy that is released. Yeah, more energy that is released. So it is harder to add on the phosphate than on oxygen, when usually would say that it is more exothermic to the right, which means it's easier on the right. Well, actually, that does not contradict. Either way, just remember that adding an electron and oxygen is easier than the phosphorus. Sometimes our textbook is a bit controversial. Just oxygen is easier to add than phosphate. So metallic character is the last one. Metallic character is very simple. It's the same as the radius, and honestly this is kind of intuitive, but anything to the right and to the bottom is more metallic. And that's it. I think we'll stop here for this video. So everything about configurations and periodic table.